All right, these are the video notes for section 3.7. Today, basically what we're doing, like I mentioned to you guys yesterday, is we're just moving on with another family of functions, which is absolute value, and we're going to keep doing the same thing and add on one more thing. So we'll do left, right, up, down, we'll do reflection, and then the additional thing today is the dilation. And I'll get to the dilation in a little bit, but let's just do a little recap of the stuff from previous days. So as a reminder, at the top of the video, at the top of the slide there, you see left, right, up, down. We should have that down pretty well by now. Everything we do is really coordinate based, so we try to focus in on a vertex, and that vertex helps us from the parent graph to the translated graph to understand what the movements are. So if you look at the blue vertex or the blue graph, the f function, that's a 0, 0, which typically would be our starting point. So when we look at a graph that has no translations, no movements, it would be a vertex at 0, 0. Now you look at your other vertex, looks like we're at 4, -5. So remember, 4, -5 describes a movement. 4 is right 4, -5, down 5. Fairly easy to do. As you translate from vertex into equation, remember that the x has the opposite sign. And if you think of it working off of the generic version of this, when you put in 4, it's going to be x minus 4, which will actually be right, as a right movement. So, pretty simple. Take your vertex, plug it in, you're good to go. Remember that our k movement, our up-down movement, is exactly what the number says. From coordinate to equation, there's a sign change, but actually if you just plug it in as is and you go x minus, insert your h, that'll take care of it for you. Same thing if h was negative. Let's say it was a -4 and you insert it into that purple equation, it would be minus a minus plus. So if you operate off of the general form, that sign change will just sort of happen as you plug it in. So left, right, up, down. Fairly simple idea from the last couple of days. I think by now we should all have that. The other idea that we had on yesterday was reflection. And this one is maybe a slightly bit more to think about and keeping it straight. I think left, right, up, down, once you do a few days of that, you're good. Reflection really is about where I place the negative. And so from yesterday, if it reflects over the x-axis, we said you should attach a negative to the function, which means it goes outside whatever function you're dealing with. If you reflect over the y-axis, you should attach attach a negative to the x value, which are reflected over the y. If you ever get them confused, think about it as a single coordinate. How does a single coordinate move? So for example, if I'm right here and I move that coordinate to here, what changed? Well, it has the same x value, the y value changed sign. So if you change the sign on y, you reflect over x, and vice versa for the other. Now, again, as a left, right, up, down idea, we want to think about it as where's the new vertex at? So if you look at your red as a coordinate, you had -3, -4. -3, -4 describes the movements for me perfectly, so I can see visually clearly it's left and it's down. So when I go to write my equation as a root function. Now here's the idea, if I actually did it as minus h and I put in -3, that would take care of the plus for me. I think at this point, a lot of you guys probably are going to keep it, sort of have it memorized that it's opposite when you go from coordinate to equation. But if you did it as the general form and plugged it in, you would get the right side. And then your k on the outside. The other piece of this is the reflection and which type I have. So if I think of the red graph, I'm going to kind of draw over it for a second, and I move it back over here to get a look, then I can tell clearly that's been reflected over the x-axis. So a reflection over the x, and then I have my movements. Right 3, down 4. So if it's reflection over the x, where does the negative go? That'd be out front of the function. So now I've written a reflection with a left and a down. Again, it's just practice, right? You guys get lots of practice of this during this chapter for sure. It's all about, mainly, it's all about transformations. Okay. Well, then there's the new idea. And the new idea, or the addition to doing the different kinds of transformations, would be a dilation. Dilation changes the size of or I should say changes the shape of an object. And when we do that, it's going to be a horizontal or vertical change, and usually we say by a factor of. The scale factor means you increase or decrease its size by how much. So for example, if I say it's twice the size, the scale factor is 2. Half the size, scale factor is 1/2. So visually what we're going to see in a graph is the idea of the graph basically getting wider or narrower. Now, also, to explain the idea of dilation, we're going to use a new function. So we've been doing line, then parabola, quadratic, then root, today absolute value. And I think it's easiest to see with an absolute value graph to see the dilations happening, because you can watch the shape of that graph change, widen or narrow pretty easily. So the first thing we need to do is discuss a little bit of just what's the absolute value graph look like. So every day as we do a new family, a new function, we talk about here's the basic or the parent. The parent is the graph that has no transformations, no shifts, left, right, up, down, no reflection. It's just your standard graph. I don't know if you guys remember much about absolute value or not, but you have had it before. When we talk about absolute value, we think of it as positive, as a distance almost idea. So you can take the absolute value of any number and it will produce a positive result. So the absolute value of 0 would be 0. The absolute value of 1, 2, 3. But when you go to -1, it's also 1, 2, and 3. So the concept of absolute value is when you do the absolute value of a number, it will always produce a positive result. Because that's what's happening as you watch the coordinates light up, you can see you get that kind of symmetry going on like you have in a parabola. You got a left and right side that look the same. You have an axis of symmetry. You have a vertex. All those ideas are there again. Vertex at 0, 0, and left, right sides look the same. So when you're plotting points, if you have to draw a graph of this, it's pretty easy to get going. Really, you have a slope that is positive, negative on each side. If I start at 0, 0 and go up 1 over 1, that draws the right side. Go up 1 and to the left 1, the opposite direction, draws the left side. So absolute value and quadratic, very similar kinds of graphs. So there's the parent function. That's the graph we want to work off of to do all of our transformations. Let's start going through and doing a little bit of translation. So translation, left, right, up, down, and we'll do a little reflection too, so we kind of get that all going. And then we'll build in the dilation as the last piece of the puzzle. So when we look at our function, our general version of it, kind of generic form, it has that look that we're used to when it was quadratic. We had that when it was root function. We had that, and now we've got absolute value. So really it's the same idea, but a different looking function, a different style. So if we start out working with our vertex as our guide, which it always is, right? We got 0, 0 with our parent. So there's our parent function, the red, or the A graph on your note sheet. If we go to the B graph and check out its vertex, that's a -5, 2. Sorry, -5, -2. So visually I can tell, clearly it's to the left 5 and down 2. So now I go insert those changes into my absolute value. My absolute value symbols will be the grouping symbol. I do not need a set of parentheses. That's only when you do quadratic. Just like a root function, you don't need a parenthesis for a root because the root is the grouping symbol. So here what we do is we do absolute value. Now if I have a x minus h, but my h is negative, minus and minus is plus, or I know probably now, I haven't done this for 3 days, that when I go from coordinate to equation, sign changes. And then my -2 tacked on to the end. When I go to do the C graph, I can tell there's been a reflection. So if I think about, do black here for a second. If you look at the red graph, there's a reflection of it over the x-axis, and then that's been moved. I didn't draw that perfectly, but you get the idea. So I can see a reflection over the x. I'll have to build that in, and then also a new vertex. So if I'm thinking about where that vertex is at, looks like I'm at 4, 2. So for my C graph, what I could do right away is go absolute value. Knowing that it's at 4, 2, x minus h plus k, and then where does the negative go? Remember, reflection over the x-axis is a change in y, which is really a change in the function's value. So the negative goes out front. So absolute value compared to the other days, very similar and very just as easy as the others. Put in your left, right, up, down. Put in your reflection. Not really going to make it any more difficult. Now, the last pieces that we do, which is dilation, I think is fairly easy too if you stick to the coordinate idea behind it. But I think it's a little bit harder the first time you do it to grasp. This stuff, you can look at it and go, clearly I can see left, right, up, down. Clearly I can see a reflection over a particular axis. Dilation, you have to kind of sort of think about, well, what does it mean? And when I look at it, how do I interpret that a little bit? And it's a little bit harder, but not bad. So what we need to do first is just describe how they happen. And you got 2 types. There's going to be a horizontal and a vertical. And what we call it is a stretch or a shrink. If you stretch it out horizontally, the graph would get wider. So as an absolute value, basically it would open up like a mouth opening up. It would get narrower if it's a shrink. Vertically is a little bit harder to kind of visualize. You'd have to think about it as though here's your absolute value. And if I could grab this and this and this at the same time and just sort of pull it apart, top to bottom, that would stretch it out vertically. If I could think of it as like my hands are, one hand's on top, one hand's at the bottom, and I squish it together like a sandwich, that'd be a vertical shrink. That's a little bit harder to visualize, but